At this point in the course, we are looking at the distribution of our sample statistics, x bar, p hat, and s squared. And that is, we want to know how they behave. We've already established their means and standard deviations where we can. And so x bar, the sample mean, s squared, the sample variance, those two are handled in other videos. This video is going to focus strictly on p hat, the sample proportion. Now, the proportion is always related to some particular event happening. It's the proportion of times that something happens when you do an experiment. Okay, so if P is the actual proportion or probability of that event happening, we know that the mean and standard deviation of P hat are directly related to that true probability or proportion that we covered earlier in the course. Now, before we can get into the distribution of p hat, there is one other thing we need to talk about. What should you expect to happen when you do the same experiment over and over again? Okay, so specifically, how many times should you expect to see a given outcome? So if the probability of doing an experiment and in getting a specific outcome is p, every time you do the experiment, the probability is p over and over again, and the results of each experiment are independent, and we do the experiment n times, then we would expect that event to happen approximately n times p times. Now, n times p, that's the number of times the experiment's done times the probability or proportion of times the thing is going to occur. So you're used to this. If I asked you, what is 27% of 149? You would take the 149 and multiply it by 0.27, because multiplying by that proportion, 0.27, is going to tell you what 27% of the given number is. That's all this n times p is really doing. So let's look at a couple of examples. Flip a fair coin 100 times. How many times should you expect the coin to land heads up? So n is 100, p is 0.5. There's a 50% chance of getting heads each time. So we need to know what is 50% of 100. We take n, 100, times p, 0.5. 100 times 0.5 says what is 50% of 100? And of course that's 50. You already knew that. That's not the revelation here. It's the n times p. That's how we calculate how many times we expect to get a particular outcome. As we've discussed, though, several times this semester, samples rarely match the population perfectly, so we expect to get somewhere in the neighborhood of 50 heads. So we might get 48 heads, 52 tails, maybe it's 55 heads, 45 tails. But it's very unlikely that we'd end up with 3 heads, 97 tails, based on this estimate. Okay. Now, looking at a second example, what if we roll a fair die 600 times? Roughly how many sixes should we expect out of those 600? N is 600, P is 1/6, so we would expect roughly 1/6 of those 600, so 600 times 1/6, N times P, about 100 sixes. So we roll the die 600 times, sometimes it is a 6, sometimes it's not. We would expect somewhere around 100 sixes and around 500 other numbers. So early in the semester, we've talked about this multiple times. The mean of the p hats is equal to the actual probability of the event happening, right? So if we're talking about flipping that fair coin, the real probability of getting heads is a half, 0.5. So in some samples, the proportion will be less than a half are heads, other samples more than a half. But when we average out all the sample proportions, we should get exactly a half for the average of those p hats. And similarly, the standard deviation of p hat, so how spread out the sample proportions are, is directly related to the probability of the event happening and the sample size. It turns out that p hat is never actually normally distributed, unlike x bar. However, P hat can sometimes be approximated by a normal distribution, but only when n times p hat is greater than 5 and n times 1 minus p hat is greater than 5. Now I want to remind you what p hat is. P hat is your sample proportion. And to calculate p hat, you take your frequency and you divide it by your sample size. So when you take n, your sample size, you multiply that by the frequency, divide by the sample size. The two sample sizes cancel out. And so n times p hat is just the frequency of times the event does happen. P hat is the proportion of the sample where you get your particular event. 1 minus p hat is the proportion where that event does not happen. So n times 1 minus p hat is just the frequency of times where your event does not occur. So all this is saying is in our sample, whatever it is, we're flipping a coin, we need at least 5 heads and 5 tails. We're rolling that die, we need at least 5 sixes and 5 that are not sixes. As long as that's true, then p hat can be approximated with the normal curve, and we can use all the tools from a normal distribution that we're used to. The problem is we often want to know the distribution of p hat before we've collected the sample. Right? We want to know what are the chances that p hat does something. Now, if you haven't collected the sample yet, you don't know what p hat is, so you don't know what n times p hat is going to be. So that's where our expectation discussion from a few minutes ago comes in. If you haven't collected the sample yet, you don't know if you have at least 5 that are and 5 that are not in your category. So you have to see if it's reasonable to think that it will likely happen. And so we check n times p. If n times p is bigger than 5, that means you expect more than 5, whatever it is you're looking for. And if n times 1 minus p is bigger than 5, then you are expecting more than 5 times to get that outcome. Okay, so this is a little bit subjective in the sense that what happens if n times p is 5.1? That means there's a good chance p, the frequency, won't turn out to be bigger than 5, so that would be real iffy. But if n times p is 800, even if your sample doesn't match the population very well, you still know you're going to get way more than 5 of that particular outcome. And so that's what we're talking about here. We need to have a reasonable expectation that the frequency of times that you get your event happening is going to be bigger than 5, and the frequency of times the event doesn't happen is also going to be bigger than 5. As long as that's true, we can use all of our normal distribution tools to approximate p hat. In this first example, we're going to roll a fair 12-sided die 19 times. And we want to know the probability that more than 50% of those 19 rolls turn out to be multiples of 6. Okay, so the variable here is the percentage of rolls that are multiples of 6. Percentage and proportion are directly related. So what we're really trying to find out here is what's the probability that p hat is greater than 0.5. If the proportion is above 0.5, the percentage will be above 50%. So we need to know the distribution of p hat. If this was X bar, we would look to the parent population, the population being sampled from, and ask if that population is normally distributed. Okay, but that's not the case with p hat because everything is different here. Every time we roll the die, we're interested in either we do or we do not get a multiple 6. And so we only have 2 categories for our results to be in. Multiple 6, not a multiple 6. That's not a numerical variable where most of the values are close to the mean and they fall off symmetrically in each direction, right? Every question about proportion or percentage is the proportion or percentage that fall into a category, and you have only 2 options, in the category or out of the category. Okay, so if we're going to determine the distribution of p hat, we have to look at the frequency of times that we get what we're looking for in our sample. Okay, so we said a minute ago that p hat would be approximately normal if you had a frequency of at least 5 outcomes that were in the category you're looking for. So that means we need at least 5 multiples of 6 in our sample of 19 rolls, and at least 5 that are not multiples of 6. The problem is we haven't rolled the die yet, so we don't know how many multiples of 6 we're actually going to end up with. Okay, so since p hat is unknown, the frequency of multiples of 6 is unknown. So we have to check to see, is it reasonable to expect that when we do roll the die 19 times, we would have at least 5 that are and 5 that are not multiples of 6. Okay, now we're not saying is it guaranteed, but at least is it reasonable to believe that we will end up with at least 5 that are and 5 that are not multiples of 6. Okay, so our two options for p hat is either p hat is approximately normal or it's not. Okay, and that is, we have to figure out, is it reasonable to expect at least 5 of each outcome or not? So we need to figure out n and p, do our multiplication, see what happens. So sample size n is 19, probability of getting what we want, which is a multiple of 6, 12 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Only 2 of those 12, 6 and 12, are multiples of 19. Okay, so we have approximately 19 times 2 twelfths, or a little over 3.166 repeating. Okay, so it's reasonable to expect roughly 3.1 or a little over 3 multiples of 6 out of our 19. Which leaves 19 times 1 minus 2 twelfths, or 15.833 repeating. Okay, so it's reasonable to expect that we would have a little more than 3 that turn out to be multiples of 6, and about 15, 16 that are not multiples of 6. Okay, so those are not both bigger than 5. Okay, so it's unreasonable for us to believe that we will have at least 5 that are and 5 that are not multiples of 6. So we cannot say that p hat is approximately normally distributed. Okay, so we're left with the distribution of p hat being unknown, meaning if this probability that p hat is greater than 0.5 was a probability I needed to figure out, we wouldn't be able to do it with the tools that are in this class. Okay, this time we're going to look at a slightly different die example. We're going to roll a fair 6-sided die 200 times. And we want to know what is the probability that less than 40 of the rolls are ones. So that's the probability that less than 40 out of 200. That's a proportion of a sample. So we want to know what is the probability that p hat is less than 40 over 100. Okay, so to find that probability, we need to know the distribution of p hat. In the population that we're sampling from, every number either is or is not a 1. So that's not normally distributed, and that does not matter. Okay, we don't know how many ones we're going to get because we haven't rolled the die yet. So we have to look, is it reasonable to expect at least 5 out of the 200 rolls to be ones and at least 5 not to be ones? Right? So we have our two options. Okay? And because p hat is unknown, we're going to check n times p and n times 1 minus p and see if they're both bigger than 5. So n is the number of times we roll the die, 200. P is the probability of getting a 1, which is going to be 1/6. So n times p, 200 times 1/6 is about 33. And 200 times the probability of not getting a 6, okay, so that's 1 minus 1/6, or 5/6, is about 167. And again, I could just do 200 minus the 33. Once we know that that's 33 roughly, we don't know that we're going to get exactly 33 out of 200 because the outcomes are random. But we expect it to be somewhere in the neighborhood of 33, which means it's very unlikely that we won't get at least 5. Okay, so we expect, all right, about 33 of the rolls to be ones and about 167 to be something other than a 1. Both those are more than 5. Okay, so we are good to go. p hat is approximately normal, right? And to find this probability, we'd use all the tools that we usually use with a normally distributed variable. Let's talk some history here. Peyton Manning attempted 1,381 passes as the quarterback at UT. Of those, 863 were completions, and 89 of those completions were touchdowns. If you randomly pick 10 of his pass attempts from that 1,381, what's the probability that less than 7 of the 10 you pick are completions? Now, another way to say that is, what's the probability that he completed less than 70% of the passes in your sample? So we want to know what's the probability that p hat is less than 0.7. We need to know the distribution of p hat. Right? We don't know which 10 completions you're going to get. So when it comes to the distribution of p hat, right, we don't know the frequency. We don't know if we have at least 5 that are and 5 that are not completions. Okay, so we have to decide if it's reasonable to expect to have at least 5 that are and 5 that are not in our sample. And to do that, we're going to start with n times p. And p hat's unknown. And n here is how many times we do an experiment. And our experiment here is picking a pass and seeing if it's a completion or not. So we're doing that 10 times. And every time we pick one random pass attempt, the probability that it's a completion would be 863 out of 1381. So n is 10, p is 863 divided by 1381, which is about 6.2, okay, which leaves us, I can use the formula or just do 10 pass attempts, 6.2, and subtract that from 10, I get 3.8. Okay, so if we pick a random set of 10 passes, we expect around a little over 6, so about 6 completions of the 10 and 4 that are incomplete. Okay, that's not more than 5 of each. Okay, so p hat is not going to be approximately normal, and we're stuck. Period. We don't know the distribution of p hat, so we cannot find this probability. This time we're going to ask a different question about Peyton Manning's time at UT. So if we randomly pick 100 of his completions, what's the probability that out of those 100, somewhere between 6 and 12 are touchdowns? Okay, so we want to know the probability that the proportion of touchdowns is somewhere between 6 out of 100 and 12 out of 100. That's what we're asking. And to find this probability, we need to know the distribution of p hat. The population we're sampling from, again, either every pass, every completion here either was or was not a touchdown. That's not normally distributed. It's either touchdown, no touchdown. So that doesn't help us in the distribution of p hat. We don't know which 100 we're going to pick because we're randomly picking them. So we don't know how many will or will not be touchdowns. That's the entire point of this problem, is that the proportion of touchdowns is undetermined as of yet. Okay, so we don't know the frequency of touchdowns in our sample. Okay, so we have to check to see if it's reasonable to expect at least 5 touchdowns and 5 non-touchdowns. Okay, again, that's because p hat is unknown. The sample frequency f is unknown. Okay, so we're going to have to estimate p hat with p here. Okay, so n is the sample size, and we're randomly picking 100 completions, so n is 100. And the event is getting a touchdown. So given that it's a completion, because we're only picking from the completions, what's the probability that it's a touchdown? Okay, so 89 out of the 863 completions were touchdowns. So with that, n times p is roughly 10.3. And again, we can use the formula, or we can do 100 minus 10.3 is 89.7. Either way, it's reasonable to expect somewhere in the neighborhood, give or take, about 10 of the 100 to be touchdowns and about 90 that are not. Okay, so 10 is definitely, higher than 5. We're not looking at 5.3 or 6 or something really close to 5. Okay, so we're going to be fairly confident that p hat will be approximately normally distributed, and because it's reasonable to expect that we'll have at least 5 touchdowns in the sample and 5 that are not. Okay, so p hat is going to be approximately normally distributed. And so to find this probability, we would use all the tools that we usually use when something is normally distributed. And that's going to come a little later in the semester. Not very long though, so get ready for it. Okay, so that's p hat. The distribution of p hat doesn't depend on the population that we're sampling from being normally distributed. It depends on whether or not you expect to get at least 5 values in your sample that are in your category and 5 that are not.